discussed. What about the light? Okay. Yeah. So we have been discussing this. Maybe you can even sit on one side because you will be. I can only show on one or the other. You know, it is good. We don't have so many people. You know, maybe you can sit on one side. So we have been discussing these perturbation methods only very briefly, just to show that we can describe system where we don't know how to solve the exact wave function of a Hamiltonian, which is quite complex. Okay, so we have been showing that if we know the solution of one Hamiltonian and we don't know the solution of this one, then we can solve it in a form of perturbation, and we can solve first perturbation, second, third, and so on. But I don't do it here, and this is true for energy and for wave function as well. Okay, so then the first correction for energy would be calculated like this, where I take this Hamiltonian, which is like small corrections to the one which I know, and average over the wave function of the known Hamiltonian. Okay, and we can calculate also the first order correction to the wave function, but I didn't do it. It's just too complex for us now. Yeah, so this is one method which we can use, and another one which is actually more important for us is this variational method, which essentially searches the solution in some kind of random search of, let us say, wave functions, where we have some coefficients which we optimize, okay? And we have a way how to optimize it because there is this variational theorem which says that the better the wave function is, the lower the energy calculated with it is, if I say it like that, okay? So if I take some wave function, whichever I take, calculate the energy in this way, then the energy will be the lower, the better is the wave function. The closer is the wave function to the correct ground state. Okay, so the ground state wave function, if this is the exact ground state wave function of this Hamiltonian, and this is the exact energy, then this is the exact energy. So for the ground state wave function, the energy which is kind of lowest. Okay, this energy is the lowest energy which you can get in this way. Okay, so that means that any wave function which is different from this will have energy which is larger than E0. Okay, do you get it, right? So and the closer the wave function look like the correct one, the closer this energy will be to the exact energy. Okay, this is the theorem. So then I don't want to go again this proof, right? So in that sense, we can try to expand the wave function in some set of trial wave functions. So basically, what I do, I take a complete basis set. For example, I take a complete basis set of an electron wave function, which I just discussed in the previous lecture, right? 2 minutes ago. And then I expand this wave function in this electron wave function and optimize the coefficients. And if I have a complete basis set and optimize it, I will get exact energy, exact wave function, exact energy. If I have incomplete, if I just take few terms, then optimize it, I can get something which is close to the exact wave function, but it would not be exact, right? So basically, I take, for example, Slater determinants, and then superimpose Slater determinants. If I use a complete basis set of Slater determinants, all of them, then optimize the coefficient, I will get exact solution of an electron system. Okay? With the Hamiltonian which I have for an electrons problem. This would be an electron Hamiltonian. I optimize the sum of the Slater determinants, and I will get the exact solution of the electron problem. Typically, it is impossible to do it. So I will just take, let us say, 100 Slater determinants in a computer. In some way, I prepare it, and then I optimize 100 coefficients, and I will have a solution which is precise, maybe with 2 or 3 digits in the energy. which is very good actually. It's excellent. It's an extremely good solution. Okay, so that's the way how we proceed. And when we have such a solution, what we search is the minimum of the energy for the. If we want to optimize these coefficients, we search for the minimum of the energy, where the derivative of the energy over these coefficients is 0, and then it gives us this set of equations, these secular equations, which when we solve them, we will get the solutions for the coefficients. Okay, we will get these coefficients from this. Typically, we will get more than, if we have more than one term, we will have more than one solution like this. But the lowest energy solution would be a kind of good approximation for the ground state. The first, the next solution would be good approximation for the first excited state. The next solution, right? So if you put here 100 wave functions trial, usually you will get an approximation for, let us say, the first 20 quite good, okay? If you have a rich basis. So that's how we can proceed, okay? So and then in this way we can search the wave function for atoms or molecules, and that's the method of this LCAO-MO, linear combination of atomic orbitals into molecular orbitals, right? Variational method. Yeah. Okay, so then we had one lecture which was kind of summarizing the electronic structure of atoms. I don't dwell on it much. You can say something. Composite spins, and then even combine those two, and then we associate, we find some new states which are associated with the combined L, combined S, and combined J, which is L plus S. Okay, and this procedure essentially is necessary because spectroscopically, when you try to see the spectra, you observe transition between states which are defined by those three numbers. Okay, because those are the stable, those are the well-defined eigen, the eigenstate of the Hamiltonian commute, or the Hamiltonian commute with those, let us say L, S, and J plus L. It doesn't commute exactly with each of them, but it commutes with this one approximately, with this one approximately, but it doesn't commute with this one, okay? So that's why if we find eigenstate of this and this, we are having quite good spectroscopically many electron states, and then we can observe them in the transition. So we characterize them by some by some indexes, right? I don't want to go through the way how we construct them. We have a configuration of electrons, and then from the configuration we can construct eventually basically different levels, states, right? And they are terms, levels. So configuration gives you term gives you levels, and then states. So we can assign the L, whatever it is, we can pick it here. Then the S, whatever it is, we can put it here, and J, whatever it is, we can put it here. And these angular momentum. The electronic terms actually are defined like this, and then with different L, J, and S, they are split. Okay, still. So if you know some L, J, and S, they are split, and the splitting comes. So you see that this is a configuration. Configuration gives me two terms. This term gives me this level. This term gives me three levels. This level gives me these states. These states. Okay. So you can see spectroscopically, if I don't have a magnetic field, then this is what I observe spectroscopically. Okay. If I have magnetic field, I observe spectroscopically this. Okay. Those are the combined states that form in the atoms. And it is because these are the concept. If I don't have electron-electron coupling, this is fine. When I include electron-electron coupling, I have these terms which form, and they are split according to the spin. This is the singlet, this is the triplet. when you have spin orbit coupling, also the J, total J, actually is split, you see. This is the spin orbit coupling Hamiltonian, we discussed, it's here, right? The spin orbit coupling is giving us the splitting. And the magnetic field also splits the J into MJ, right? So it is very, very clear. Well, obviously, if you do it by hand, or the construction of the state, it's not such a peanut, but it's doable. It's just the technical stuff. Yeah. All right, so those are this is spin orbit coupling, which essentially interaction between spin and angular momenta, right? They generate separately the magnetic field, and then they interact and they lead to the splitting. Yeah, and this is the magnetic field interaction. Okay, and then there are some phenomenological rules, which are called good rules, which basically tell us which of these states are which energetically, how are they positioned one respect to each other. So if I start from a given configuration and I obtain all the possible states, these rules tell me which of the states are lower in energy and which of them are higher. And these phenomenological rules essentially tell me how much kind of freedom is in these states. So the more freedom actually the state has in terms of kind of complexity, the more the electron can get farther away, and then the lower the energy is. When they are kind of confined, there is not much freedom, then they need to be close, and then they are very high because the electrons repel each other. Okay, so that's the principle, roughly speaking. Okay, the spectroscopy, I think next week the student will talk with you, the graduate student will tell you 2 lectures about the spectroscopy. He will continue what I started with. I had 1 lecture, so he will tell you something about the vibrational selection rules and the rotational selection rules. Okay? Yeah. Okay, so then the molecules essentially same stuff like for the atom, except so we again do the Born-Oppenheimer approximation. We freeze the nuclei, and then we can then separate the total wave function of the electrons and nuclei into a product wave function where electron wave function is multiplied by nuclear wave function. If you don't do this Born-Oppenheimer approximation, the coupling of electron and nuclei, I mean, this is this term, right? Electron-nuclear coupling leads to this entanglement. Again, it cannot be written like a product. So this would be a terribly complicated wave function where electrons and nuclears are kind of mixed, and you would have, the wave function would look like this. You would have 1 nuclear wave function, 1 very complex electronic wave function, plus 1 nuclear wave function multiplied by 1 electron wave function, plus 1 nuclear and 1 electronic. And you cannot write this sum like a product of 1 nuclear multiplied by 1 electron. You see, it's again very, very complex. Yeah. So this is the kind of solution that we have. And once we do the approximation, then we basically fix the position of the nuclei, and we are solving only the electronic problem. Okay. So for fixed positions of nuclei, which are acting like a parameter. This is like a potential well. You basically say, okay, my potential well is determined by these positions of the nuclei. And now you solve the many electron problem in this potential well. Okay? And the electrons are moving, jiggling all of them together in this potential well. So then what I get once I solve it, right? I get the ground state of the electrons in this potential well, the first excited state, the second excited state, and so on, right? And we know this is this hypersurface or so, and once we get this potential energy surface, then this is actually calculated for different distances of the nuclei, right? So for each position of the nuclei, for each kind of potential well, you get 1 point. And as I change the distance, then I get different values, and you can kind of plot it like a potential energy surface. So then once I calculate for different distances of the nuclei the potential energy surface, I can use it like a potential energy in the problem of the nuclei themselves. So then I take the kinetic energy of the nuclei, this potential energy, and solve this nuclear Hamiltonian, and then it is essentially like one particle problem or several particle problem of nuclei moving in this. So for diatomic, it would be like two nuclei with coupling between them, which is given by this coupling energy of the electronic type, right? So then we can solve this nuclear problem, and what we get for the atomic would be the vibration, right? And we get also the rotation of the nuclei. So then if we can separate it, which is not always the case, but if we approximately separate it, then we will get the nuclear wave function. I mean, this is the translational, which I can forget about, and then this is the vibrational part, and then this is the rotational. Okay? So that would be basically giving me these vibrational degrees of freedom and the rotational degrees of freedom of the diatomic, right? There is one vibrational degree of freedom and two rotational, actually. One actually. All right, so then we have electronic, we would have electronic degrees of freedom, vibrational, rotational, okay? Yeah. Yeah, two rotational, yeah. So then, I mean, we can solve it, I return back to the electronic, so we can solve exactly this problem which we have here, we can solve exactly for one electron we can solve it exactly, but this is only H2 plus, very simple case or so. So it is known what the solution look like. And otherwise we can solve it by, again, some variational method. So if you have more, this is the exact solution. If you have more electrons, we again would start with some Slater determinants, right? Basis set of Slater determinants and superimpose them. Yeah. Yeah. So for example, if I want to, just to give you some practical example, if I want to solve, let us say, H2, I think it is actually shown here. If I want to show H2 molecule, right? H2 molecule in the Hartree-Fock method, okay? Hartree-Fock method means that I choose one Slater determinant, right? And one Slater determinant for two electrons would be this, okay? And then I want to optimize this one Slater determinant, so I can optimize these wave functions which are in the one Slater determinant, and after the optimization, I find the best one Slater determinant which describe the hydrogen molecule. Okay, so then I can use the variational method to describe the wave function, right? I can actually find some superposition of these wave function in a form of atomic states, and then solve it, right? So I mean, we did it better for H2 plus, which is just one electron. So in that case, it is not a Slater determinant; it is just one wave function. And then optimization of these coefficients, like superposition of atomic states, give me, after I solve it, it gives me two solutions. One is the ground state, which is symmetric wave function, and one is the anti-symmetric. So if I have plus, it is symmetric. If I have minus, it is anti-symmetric. Okay? And that's what I get approximately. Of course, exactly it would be slightly different wave function. Yeah, and then we discussed a little bit the symmetries. You can look on it if you want. There are all kinds of symmetries of these wave functions. And again, the states can be then characterized depending on the symmetries, and we can then construct the molecular states in a similar way. We can go and denote, this is the population, how we populate them, but we can then denote again, like in the atomic terms. We can define electronic terms for molecules, and again build some kind of terms which would be stable, and states which would be stable, and quantum numbers which would be stable. And for different molecules, the quantum number needs to be defined differently depending on the symmetry of the molecule. If it's diatomic or if it has different symmetries, so there would be different kind of quantum number which would be more appropriate according to the symmetry, and then those states would be stable and spectroscopically visible. Okay, so I guess that's about all what I wanted to say about these molecules. Yeah, and of course the calculation, if you do it, you can also get a vibrational motion, and you can calculate all these vibrational states. From the potential energy surface, when you know how the potential energy surface look like, you can calculate all these frequencies of the vibrations which the molecules has. We can do the normal, we can find the normal modes and find how the molecule vibrate. There are, I don't know, 3 and -6 modes, vibrational modes, and then we can find how they vibrate and what are the frequencies. So this is all possible and very useful, because then spectroscopically we can get it. Okay, so I don't know, that's all for the molecules. So I'm done with the molecules, and I'm done essentially with the quantum part. Okay, so then we have the spectroscopy, right? And this is what we discussed already recently. We had an exam recently, so I will go a little bit faster about over it, right? So do you have any questions to this? So really, the basic stuff about the quantum, I would say, as I just said, okay? Yeah. So the spectroscopy should be kind of more familiar to you, because we had an exam just like a week ago, right? So I don't know, I mean, I don't want to go over what you had in an exam just 3 days ago, but we have to now consider, basically, we now assume that you have some objects which you want to describe by the statistical mechanics. Those objects typically would be molecules, atoms, either in gas phase or, I don't know, proteins, whatever you want to biologically tell me, can fit here. You can put lipids in membranes, and you can describe them by these statistical mechanics, right? So that's fine. And we just need to kind of find the quantum states of these molecules, each of them, right? So in the gas phase, it's kind of simple. In the solution, it is much more difficult, and describe statistical mechanics of solution is something which we would have to do in some statistical mechanical advanced course, not in the one which we do. This is more like for gas phase case, you know, the discussion. But the principles are the same, okay? So we would need to find the microstates which are in the system of those particles which we have, right? So if I consider just maybe some, I don't know, 6-electron atom, but it can be a molecule or 6-electron molecule, right? But then in the case of molecules, you would have to include also the rotational, vibrational degrees of freedom in these microstates, right? So every rotational, electronic, vibrational kind of is one microstate. Set of states, one electronic state with associated vibrational, with associated rotational state is one microstate, right? And so on. So, and then if you have n molecule, that let us say 2 molecules, so the electronic of those two, the vibrational of those two, it would be one microstate of the whole composition. So it would be quite complex in reality. But, yeah. So anyway, so if we have such microstates of particles, we need to still consider if they are distinguishable or not. We can kind of form an ensemble which is appropriate for the equilibrium that we work with. If it's under thermal conditions, so it would be canonical ensemble most likely with a fixed number of components here. And then we need to consider microstates of different energies in the canonical ensemble. And we know that microstates of different energies, total energies, would have probabilities different, but microstates of the same energies would have the same probability, right? So, and the energy of the probability of the microstate would be the exponent P e to minus energy of the microstate divided by kT. That's what we got from some kind of optimization of these distributions. Okay, so then, as I said, we have different microstates. Typically, canonical is the most suitable, and we can calculate then the population, the probabilities of these microstates, and we need to find how many of these microstates we have for every energy, and then from this we will be able to get everything, right? We can then get the distribution of the particles in the individual levels, and we can get much more, all the thermodynamics. So the distribution of particles, for example, in individual levels, if they are distinguishable, we get the Maxwell-Boltzmann distribution, right? This is the Maxwell-Boltzmann distribution, or Boltzmann if you want. And for the quantum particles, because we don't have these degeneracies, it's kind of degeneracy. Right? So we have a slightly different distribution. Right? This is the Fermi-Dirac and Bose-Einstein. So we have like this one would be the Maxwell-Boltzmann. This is the Bose-Einstein and Fermi-Dirac distribution. Right? Those are the three. And if you cool it down, then the Fermi-Dirac would be like a step function. The Maxwell-Boltzmann would be like peak where all the particles are here, and the Bose-Einstein would be similar peak, but not so much focused on the first ground state. But at low energy, at ground energy, it would be also the same, because actually at ground, these distinguishable particles lose any sense at low temperature, because at low temperature, all the particles must be treated quantum mechanically. Because the de Broglie wavelength extend, at very low temperature, all the particles need to be treated quantum. So we would have only those two particles, fermions and bosons, and we have two distributions where the Bose-Einstein distribution at zero temperature, all the particles are in the ground state. This is the condensation, like superconductivity and so. And here we have a Fermi gas, where basically all the states are populated until the Fermi energy, and then from Fermi energy up, there is no population. These are the electrons in metal, for example. The states in metal are populated up to the Fermi level, and from there they are empty. And if the Fermi level goes in a band gap, then it's an isolator or a semiconductor. Right? I was trying to say something like this. Okay, so I guess this is pretty much all the StatMech. So we have, this is the Boltzmann distribution, how we derive it for particles. We kind of distinguish the partition function for molecule and partition function for the ensemble. And then we calculated from this, for example, the kinetic distribution. So this is the molecular partition function distribution over the kinetic energies. And we calculate the velocity distribution of the molecules in a gas. Very simple. Okay, nothing much to say. Equipartition theorem. This is for every degree of freedom. Classical. This is the energy which we get. Yeah. Okay. I don't know. Is it clear enough? I try to be very, very clear. Okay. So then, yeah, this is just how we derive these ensembles. I just show you in principle by some variational method. We derive microcanonical, then canonical distribution, classical. Right? This is the distribution over the microstate. These are the microstate energies and the distribution over the probability. And this is the probability of the microstate. And then this is the grand conical, where also the number of particles fluctuate. Okay, and then we get the Bose-Einstein distribution, Fermi-Dirac, and if you neglect the one, you get the Maxwell-Boltzmann. Okay? Yeah. This is the step function, you see. And this is the same. Yeah, and then once we know these partition functions, whatever type, we can immediately link it to thermodynamics. We can connect the partition function to internal energy, pressure, and pretty much all these thermodynamic functions. Okay? entropy, Helmholtz, Gibbs energy, entropy. Everything can be calculated. I mean, you just need to derive the formulas for each case separately, but for canonical ensemble, it is obtained here. And then once you know the partition function, the canonical, then you can calculate all the thermodynamics. But this is not so easy because this partition function needs, if you want to calculate it, you need to know all the states in the system for every molecule and for all the molecules essentially, right? And then from this you get the different possible microstates, and then if you sum over the exponent with the microstates energies, then you get right. If you sum or integrate over the microstates, you get the partition function. Okay, this is the classical partition function. If you know all these microstates, or here, all these microstates, and integrate over all these, or sum over all these energies with the beta, this is essentially the same except written differently. Okay, then you get the partition function. So once you know it, you can calculate everything. Okay, all the thermodynamics can be obtained. Okay, so that's pretty much all. And then we discussed that for case of gas of classical molecules, which at room temperature can be considered classically, we can consider partition function for each molecule, and then the total partition function of the ensemble is the product of them divided by the factorial. Okay, and then we need to calculate only the partition function for the molecule, what it is. If we do it, then we know this. If we know this, we know the whole thermodynamics again of the system. Okay? So all these thermodynamic variables can be rewritten in terms of the molecular partition function now, because we just replaced the canonical partition function by the molecular using this expression, right? So everything can be now written in terms of the molecular partition function. Okay? And so the question is now how to evaluate it, and that's very, I mean, it's as difficult as before, but we can already, in principle, know. In the case of gas, for example, we just take the internal energies of the molecules and the translational energies, and then the partition function, at least for these 2 degrees, would be separable. So we have partition function for the kinetic energy of the molecule, for the internal energy of the molecule, and then because they are in product, all the function would be additive. So we would have a contribution from kinetic energy and internal energy. Kinetic pressure or pressure would be again having 2 components. Entropic would be kinetic energy, and then the other, right? And so on. Because they are in this product form, and the logarithm of this will give us 2 terms. They are always logarithms, so all these logarithms would be 2 terms, and then each of them would be coming separately like this. Okay, so then the kinetic is shown here. What it gives us, this is what we already did before. And the internal can be this again split into electronic, vibrational, and rotational, which it's not always possible, especially this is kind of questionable, these 2, but if you approximately do it, then you can have the internal molecular partition function written like a product of electronic, vibrational, rotational, right? And that can then, each of them can be evaluated separately. So the electronic is here. Typically, the molecular partition function, the molecular partition function actually tells you how many states of that degree of freedom are populated at the temperature at which you calculate it, right? That was one of the questions in the exam. Okay, so if Z is 10 vibrational, that means that you have 10 states vibrational populated at that temperature. Okay, that's the meaning of it. And so electronically, usually because the states are very far away, we have only 1 state populated, and the partition function would be this ground state. Okay, potentially if there is some degeneracy, I don't know. Okay, and then rotational, vibrational, we can also evaluate. Rotational would typically look like this. These are the rotational states and energies. So this is degeneracy and the energies, and those are the rotors, right? This is the J plus 1 number. This is the angular momentum square energies, right? Associated with angular momentum square. And then this is the degeneracy to J plus 1 of the magnetic plus minus L, right? You can do the same for spin, for anything, it's very simple, same stuff, okay? So then this is the rotational stuff, and then this is, then the vibrational is the same. You can again calculate the vibrational state. If you have harmonic oscillator without the nonlinearity, you can sum it, and what you get is this Bose-Einstein distribution again for a number of vibrations. Yeah. So we can calculate the vibrational partition function, the rotational, and get from this the contribution to the entropy from those degrees of freedom and internal energy and all the other, even heat capacity, whatever you want can be calculated. Okay, so obviously the more populated are the levels in that degree of freedom, the more chaos is in the degree of freedom, and the more entropy associated with that. So rotational, the translational has the most kind of states if you kind of decide to quantize it in some box, each molecule one box, kind of in a gas if you wish. And then rotational has less states, populated vibrational maybe just 1, 2, 3, so yeah. Okay, if you have more vibrational states, you need to consider all these degrees of freedom and use them separately and add them. Okay, so that's all. So, yeah. Okay, so I think this is the end of the statistic, right? I believe. And I believe we just had the kinetics, maybe one slide, I believe. One slide, not one slide, but one file. Let me see. Yeah, the spectroscopy is just after that. So we have the phenomenology kinetics in a couple of lectures, which we went over. This is. I guess you already did it probably in some other classes. I don't know. If not, then that's probably what would be good to know what we discussed. So we just need to calculate some reaction rates, and they are related to these coefficients, the kinetic, what do we call it, rate coefficients, right? So the reaction rate is kind of giving us the rate with which the reaction proceeds, and the rate coefficient is essentially proportional. So the rate with which the molecule disappears from the system, let us say the molarity changes in the system, is given by this rate coefficient and the molarity of those molecules in the reaction. So if I have stoichiometric coefficients 1 in this reaction, then this is the way how it looks like, right? If I have a different, I need to divide it by those. And if I have reactions where some molecule appear multiple times, then we would need to consider them in power, right? So it would be bimolecular. So, but here it is still bimolecular because two molecules need to take part in the reaction. So then we have been trying to calculate these, we describe different reactions, how they look like, and then we try to solve the population, how it changes. We discussed a little bit how this coefficient can be calculated, and so on. So this is actually very practical if you want to describe some simple reactions without really going into the details. It is very useful. But in principle, again, everything can be calculated quantum mechanically, starting from first principle, because all these coefficients can be calculated really from quantum and statistical mechanics, except that it's very complex to do all these calculations. So, I mean, we discussed some of the cases like reactions of this type or this type giving some products, and those would be the reaction rate for these two cases, right? And we studied what kind of equations, what kind of solutions for the molarity as a function of time we would get, right? So we have, I don't know, some solutions for the two cases, and then, for example, we can distinguish based on the time dependency of the solutions, which of the reaction takes part in the system. So, I don't know, I mean, for the exam, I think it would be good for a given reaction maybe to be able to construct these reaction rate equations and then say briefly how you would potentially solve it. Just whatever is in here in lectures, nothing more. And not even that, just maybe some simple case like how would you solve these two, you know. But I cannot even ask you to show me the solution. You know, it's just it's too much for you. So, I mean, maybe you can write this and then you can say some words about it. I don't know. I mean, I understand that you understand it. The problem is that you cannot derive it on your own. That's something which is difficult. Right? Yeah. Whatever. Yeah, we discussed some of these times of also. Yeah, I mean, this one is actually good to understand. Maybe, right? We have been discussing that the rate coefficient actually can be roughly understood like some kind of thermally assisted transition over some barrier, right? And this is actually the barrier. This is the minimum barrier which you can find on the potential energy surface when you plot a potential energy surface for the reactants and the products, right? So you have reactants, whatever they start with a very complex potential energy surface, and the reactants rearrange into some products, right? And the minimum barrier, which is between these two sides, the reactants and products, is the barrier which you want to overcome in the reaction, right? Whatever you find, if you want to if you are walking like a pedestrian on this potential energy surface from the side of the reactant and you want to go to the products, the minimum kind of barrier which you find is this barrier which you need to overcome. Okay? And so then the probability that you will overcome it, again, is given by this Boltzmann factor, because this is the probability that you will gain thermally such an energy, right? Because you want to thermally, I mean, if the reaction is just true at some temperature, you don't excite it by light, or you don't shoot into it by, I don't know, whatever is used in these days in the war zones, then you can just open the BDC. So then you just thermally overcome it, and this is the likelihood that you need to get over the barrier, right? Yeah. So that's what it is, and then once you get to the other side, eventually the molecule can look on the problem from the opposite side, because it wants also to go back, right? There is no reason why the molecule would not. The reaction also wants to go in the other direction, right? So then you are on the side of the products, and you want to go to the reactants. But then the barrier might be different, because here you might be in some hilly region, right? You overcome some small mountain, and then you go down to a big valley, right? And then if you want to go back, you have to climb a lot, right? So that's actually quite a big effort there, right? So then you, in the other side, if you want to go, you need to overcome this big hill, and then the likelihood will be much smaller because the energy is bigger, right? So it's much harder to go to the other side, and eventually the system will establish some equilibrium between the reactants and products, and that will be thermally populated. After the system reaches equilibrium, then you can assume that the population here and here is just given like in the microstates, right? The energy of this, AKT, energy of this, I mean, this is not this energy, this is, sorry. I mean, the energy of this and the energy of this, the relative probability will be given by the essentially distance, right? I mean, we discussed it. I mean, the question is how much are populated these and these, right? And this is given by the relative energy divided by kT, the ratio of those populations, right? That's what I was telling you. That's basically the Boltzmann distribution. So you can again assume that these are some kind of fictive levels, and the ratio of population on those fictive levels is a Boltzmann distribution, and that will be the equilibrium. Except that it might be hard to reach this equilibrium because it can be hard to overcome this or overcome this, so it can take ages, all right? It can be kind of frozen until somebody, yeah, right. So that's what we have. Yeah, so those have been some of these reactions. We then discussed some of the reactions which can be described by these equations. So, I mean, there are just a little of them. I don't know if I have to go over them. But you just go over them, you know. This is like one set of reactions. One go one way, the other go the other way. You have these coefficients, you can solve it, right? Or you have this branching, right? Or I don't know, you have one after another, right? And you have this kind of stationary state population, and we can use it. It can be useful. So this give us some of these limiting, like a bottleneck kind of reactions, right? Some reactions are very slow, and the one which is slow is kind of bottleneck where the whole process is slowed down, right? If I just close this Halstead Street, right, and put some barrier, then all the cars will be going with the speed which is determined how much I close it. That's exactly the same here, right? If this rate is small, then everybody will go with the speed which is determined by this rate. Okay? So then you can actually use this principle to simplify these equations and eventually go by the rate which is the slowest. That one will determine how everything goes fast. So, and we have been discussing some cases of reactions. So if you like to study reaction, just study all of them. So you have plenty of them here to look at. I don't know. I will probably ask you more like the principles of these, you know, and again, maybe about this stuff about the barrier, the probability, which is kind of more important, the equilibrium and the rates, how it goes, and then maybe some simple reactions, what kind of, how would you solve it in principle, okay? Something about this stationary state would be good to know. We didn't have it in exam, so maybe you can look on it more, but I would like that you take home also something from the quantum and stuff, right? Not just this reaction. So that's pretty much all. You see, that's how it looks. I don't know, so I do have more. Yeah, this is the quantum, right? I was just telling you, you have this reactant value and product value, and you find the minimum behind some kind of barrier, how you go over this, right? And you can calculate it quantum mechanically. Yeah. All right, so then I guess that's all. I'm done for now. And if you have any questions, you can ask me now, or you can send me an email, or I will be here actually the last hour before the exam, okay? So next Friday. I will not be here on Monday and Wednesday. Monday and Wednesday, the student from our group will tell you more about the spectroscopy, the selection rules for the rotational vibrational states, and maybe he can show you some, I don't know, molecular dynamics, whatever he will tell me. You can ask him questions. He knows all this, so you can ask him anything. If you are unsure about some of the other stuff that we did, you can still ask him questions. You know, he has access to the lecture, so if you want him to explain you something that you don't understand enough, just ask him. Okay? He will probably not be happy that he has to explain you something which he's not